firestorm released an estimated 1,000 times the energy of the bomb. 35. As the incendiary effects of a nuclear explosion do not present any especially characteristic features. 36. It is estimated by those with strategic bombing experience that as the city was a firestorm hazard, the same fire ferocity and building damage produced at Hiroshima by one 16-kiloton nuclear bomb from a single B-29 bomber could have been produced instead by the conventional use of about 1.2 kilotons of incendiary bombs from 220 B-29s distributed over the city. 36, 37, 38. While the firestorms of Dresden and Hiroshima and the mass fires of Tokyo and Nagasaki occurred within mere months in 1945, the more intense and conventionally lit Hamburg firestorm occurred in 1943. Despite its separation in time, ferocity and area burned, leading modelers of the hypothesis state that these 5 fires potentially placed 5% as much smoke into the stratosphere as the hypothetical 100 nuclear ignited fires discussed in modern models. 18. While it is believed that the modeled climate cooling effects from the massive soot injected into the stratosphere by 100 firestorms, 1 to 5 million metric tons, would have been indetectable with technical instruments in World War II, 5% of that would not have been possible to observe at that time. 18. Aerosol removal timescale. Smoke rising in Loch Carron, Scotland, is stopped by an overlying natural low-level inversion layer of warmer air. 2006. The exact timescale for how long this smoke remains, and thus how severely this smoke affects the climate once it reaches the stratosphere, is dependent on both chemical and physical removal processes. 12. The most important physical removal mechanism is rainout, both during the fire-driven convective column phase, which produces black rain near the fire site, and rainout after. The convective plumes dispersal, where the smoke is no longer concentrated and thus wet removal is believed to be very efficient. 39. However, these efficient removal mechanisms in the troposphere are avoided in the Robock 2007 study, where solar heating is modeled to quickly loft the soot into the stratosphere, detraining or separating darker soot particles from the fire cloud's whiter water condensation. 40. Once in the stratosphere, the physical removal mechanisms affecting the timescale of the soot particles' residence are how quickly the aerosol of soot collides and coagulates with other particles via Brownian motion, 12, 41, 42, and falls out of the atmosphere via gravity-driven dry deposition, 42, and the time it takes for the phoretic effect to move coagulated particles to a lower level in the atmosphere. 12. Whether by coagulation or the phoretic effect, once the aerosol of smoke particles are at this lower atmospheric level, cloud seeding can begin, permitting precipitation to wash the smoke aerosol out of the atmosphere by through a deposition mechanism. The chemical processes that affect the removal are dependent on the ability of atmospheric chemistry to oxidize the carbonaceous component of the smoke, via reactions with oxidative species such as ozone and nitrogen oxides, both of which are found at all levels of the atmosphere, 43, 44, and which also occur at greater concentrations when air is heated to high temperatures. Historical data on residence times of aerosols, albeit a different mixture of aerosols, in this case stratospheric sulfur aerosols and volcanic ash from megavolcano eruptions, appear to be in the 1 to 2 year timescale, 45. However, aerosol-atmosphere interactions are still poorly understood. 46, 47. Soot properties. City aerosols can have a wide range of properties, as well as complex shapes, making it difficult to determine their evolving atmospheric optical depth value. The conditions present during the creation of the soot are believed to be considerably important as to their final properties. with soot generated on the more efficient spectrum of burning efficiency considered almost elemental carbon black, while on the more inefficient end of the burning spectrum, greater quantities of partially burnt forward/oxidized fuel are present. These here partially burnt organics, as they are known, often form tar balls and brown carbon during common lower intensity wildfires, and can also coat the purer black carbon particles. 48, 49, 50. However, as the soot of greatest importance is that which is injected to the highest altitudes by the pyroconvection of the firestorm, a fire being fed with storm force winds of air, it is estimated that the majority of the soot under these conditions is the more oxidized black carbon. 51. Consequences. Climatic effects. A study presented at the annual meeting of the American Geophysical Union in December 2006 found that even a small-scale, regional nuclear war could disrupt the global climate for a decade or more. In a regional nuclear conflict scenario where two opposing nations in the subtropics would each use 50 Hiroshima-sized nuclear weapons, about 15 kilotons each, on major population centers, the researchers estimated as much as 5 million tons of soot would be released, which would produce a cooling of several degrees over large areas of North America and Eurasia, including most of the grain-growing regions. The cooling would last 4 years, and, according to the research, could be catastrophic. 2056. Disrupting agricultural production and food gathering, in particular in high-latitude countries. 57, 58. Ozone depletion. Nuclear detonations produce large amounts of nitrogen oxides by breaking down the air around them. These are then lifted upwards by thermal convection. As they reach the stratosphere, these nitrogen oxides are capable of catalytically breaking down the ozone present in this part of the atmosphere. Ozone. Diagram obtained by the CIA from the International Seminar on Nuclear War in Italy 1984. It depicts findings of Soviet 3D computer model research on nuclear winter from 1983, and although containing similar errors as earlier Western models, it was the first 3D model of nuclear winter. The three dimensions in the model are longitude, latitude and altitude. 52. The diagram shows models' predictions of global temperature changes after a global nuclear exchange. The top image shows effects after 40 days, the bottom after 243 days. A co-author A's nuclear winter modeling pioneer Vladimir Alexandrov. 53, 54. Alexandrov disappeared in 1985. As of 2016, there remains ongoing speculation by friend Andrew Revkin of foul play relating to his work. 55. Depletion would allow a much greater intensity of harmful ultraviolet radiation from the sun to reach the ground. 59. A 2008 study by Michael J. Mills et al., published in the Proceedings of the National Academy of Sciences, found that a nuclear weapons exchange between Pakistan and India using their current arsenals could create a near global ozone hole, triggering human health problems and causing environmental damage for at least a decade. 60. The computer-modeled study looked at a nuclear war between the two countries involving 50 Hiroshima-sized nuclear devices on each side, producing massive urban fires and lofting as much as 5 million metric tons of soot about 50 miles, 80 kilometers, into the stratosphere. The soot would absorb enough solar radiation to its surrounding gases, increasing the breakdown of the stratospheric ozone layer, protecting Earth from harmful ultraviolet radiation, with up to 70% ozone loss at northern high latitudes. 61. Nuclear summer. A nuclear summer is a hypothesized scenario in which, after a nuclear winter caused by aerosols inserted into the atmosphere that would prevent sunlight from reaching lower levels of the surface. 62. has abated, a greenhouse effect then occurs due to carbon dioxide released by combustion and methane released from decay of the organic matter such as corpses that froze during their nuclear winter. 62. 63. Another more sequential hypothetical scenario, following the settling out of most of the aerosols in 1-3 years. The cooling effect would be overcome by a heating effect from greenhouse warming which would raise surface temperatures rapidly by many degrees, enough to cause the death of much if not most of the life that had survived the cooling, much of which is more vulnerable to higher than normal temperatures than to lower than normal temperatures. The nuclear detonations would release CO2 and other greenhouse gases from burning, followed by more released from the decay of dead organic matter. The detonations would also insert nitrogen oxides into the stratosphere that would then deplete the ozone layer around the Earth. 62. Other more straightforward hypothetical versions exist of the hypothesis that nuclear winter might give way to a nuclear summer. The high temperatures of the nuclear fireballs could destroy the ozone gas of the middle stratosphere. 63. History. Early work. The mushroom cloud height as a function of explosive yield detonated as surface bursts. 64. 65. As charted yields at least in the Megaton range were required to lift dust forward/fallout into the stratosphere. Ozone reaches its maximum concentration at about 25 kilometers, c. 82,000 feet, in altitude. 64. Another means of stratospheric entry is from high-altitude nuclear detonations, one example of which includes the 10.5 kiloton Soviet Tesno.88 of 1961, detonated at 22.7 km. 66. 67. U.S. high-yield upper atmospheric tests, teak and orange are also assessed for their ozone destruction potential. 68. 69. 0 equals approx altitude commercial aircraft operate 1 equals Fat Man 2 equals Castle Bravo in 1952, a few weeks prior to the Ivy Mike. 10.4 Megaton. Bombtist on Ilujlav Island. There were concerns that the aerosols lifted by the explosion might cool the Earth. Major Nora Luligian USAF and astronomer Natarajan Viswanathan studied this possibility, reporting their findings in effects of superweapons upon the climate of the world, the distribution of which was tightly controlled. This report is described in a 2013 report by the Defense Threat Reduction Agency as the initial study of the nuclear winter concept. It indicated no appreciable chance of explosion-induced climate change. 70. The implications for civil defense of numerous surface bursts of high-yield hydrogen bomb explosions on Pacific Proving Ground islands such as those of Ivy Mike in 1952 and Castle Bravo, 15 Mount, in 1954 were described in a 1957 report on the effects of nuclear weapons, edited by Samuel Blaston. A section in that book entitled Nuclear Bombs and the Weather states, the dust raised in severe volcanic eruptions, such as that at Krakatoa in 1883, is known to cause a noticeable reduction in the sunlight reaching the Earth. The amount of soil or other surface debris remaining in the atmosphere after the explosion of even the largest nuclear weapons is probably not more than about 1% or so of the traced by the Krakatoa eruption. Further, solar radiation records reveal that none of the nuclear explosions to date has resulted in any detectable change in the direct sunlight recorded on the ground. 71. The U.S. Weather Bureau in 1956 regarded it as conceivable that a large enough nuclear war with Megaton range surface detonations could lift enough soil to cause a new ice age. 72. In the 1966 Rand Corporation Memorandum The Effects of Nuclear War on the Weather and Climate by E.S. Batten, while primarily analyzing potential dust effects from surface bursts, 73, it notes that in addition to the effects of debris, extensive fires ignited by nuclear detonations might change the surface characteristics of the area and modify local weather patterns. However, a more thorough knowledge of the atmosphere is necessary to determine their exact nature, extent, and magnitude. 74. In the United States National Research Council, NRC, book Long-Term Worldwide Effects of Multiple Nuclear Weapons Detonations published in 1975. It states that a nuclear war involving 4,000 Mount from present arsenals would probably deposit much less dust in the stratosphere than the Krakatoa eruption, judging that the effect of dust and oxides of nitrogen would probably be slight climatic cooling, which would probably lie within normal global climatic